Welcome to Atomic Universe. I'm Dan Bergstrom, materials scientist. Richard Feynman was perhaps the best physicist of the post-World War II era. He won a Nobel in physics for his quantum electrodynamics description of how subatomic particles behave, and was a popular lecturer as a physics professor who could clearly explain scientific concepts to general audiences. I'd like to start this series by sharing the one sentence that Feynman felt was the most important piece of scientific knowledge known to man.
I believe it is the atomic hypothesis. Well, things are made out of atoms, little particles that move around, are in perpetual motion, attract each other when some distance apart, but repel being squeezed into one another. In that one sentence, you'll see there's an enormous amount of information about the world if just a little imagination and thinking is applied.
With this video series, my hope is to show you just that, the enormous insight you can gain about the universe when looking at it from the atomic point of view. The plan for today is to review the history of the atomic hypothesis, from the ancient Greeks to modern times, and then to show you some actual atoms in action with the benefit of state-of-the-art microscopy. So let's start at the beginning. For much of recorded history, it was assumed that earth, water, air, and fire were fundamental elements that infused all the objects in the world and gave them the properties we observe, like hotness, coldness, dryness, and wetness. Today we recognize this classification system as being more descriptive of the different phases of matter rather than the composition of matter. Earth is solid phase, water liquid phase, air the gas phase, and fire is a mixture of partially ionized gases and free electrons that we call the plasma phase. We call this model the Aristotelian model, after Aristotle, who wrote in the 4th century BC Greece. It's mainly from his writings that we also learn of a rival hypothesis championed by a philosopher named Democritus, who wrote in the previous century. If you were to take an object, say a copper penny, and cut it into pieces, Democritus would argue that you can cut it into smaller and smaller pieces until these pieces are too small to be seen by eye, but you cannot continue cutting forever. Eventually, one must reach a limit where the material becomes impossible to cut further and still remain copper. He named these smallest pieces of matter atamos, after the Greek word for uncuttable. In English, of course, we use the word atoms. Democritus believed that atoms moving through the void could explain all the world we observe. For example, he believed the solidness of an object was determined by how tightly the atoms are packed in and how they hook themselves together. He also believed that the atoms come in a wide variety of shapes and sizes, and the properties of matter that we observe arise solely from the way these atoms bump into each other and interact. In many respects, his atomic hypothesis matches our modern way of thinking about atoms, as we will be exploring in future videos. Despite Democritus and his fellow atomists being so close to the mark, it was the Aristotelian view that prevailed for the next 2,000 years or so. Why is that? Well, the atomic hypothesis relied on particles that no one could see, randomly moving through a vacuum that no one could directly experience. And it depicted a random, godless universe, in contrast to Aristotle's description of objects moving with purpose according to their nature. It also probably had something to do with one of Aristotle's students being Alexander the Great, whose expansion of the Macedonian Empire spread Greek philosophy as far east as India. Alexander was also a great patron of the Lyceum in Athens, where Aristotle taught and maintained a library of his works. Through the teachings at the Lyceum, Greek philosophy diffused throughout the Roman Empire and the larger Western world. Throughout the Dark Ages after the fall of the Roman Empire, the practice of alchemy developed techniques to purify chemicals and react them to form new compounds. But any explanation of these material changes were mostly based on an enhanced version of the Aristotelian model, with large doses of spiritualism thrown in. Wood burned because it contained a fire-like substance called phlogiston. Just as the soul could be purified by ridding it of sin, so too could metals be purified into gold. A revival of atomism began in the 17th century when Galileo and his student Torricelli were able to create stable vacuums using suction pumps and inverted columns of mercury. This dispelled one of the main objections to atomism. Now that the void was a proven reality, it seemed more plausible that atoms could be moving around in it. In the next century, Antoine Lavoisier applied the scientific method to alchemy and turned it into chemistry with his publication of his Treatise on the Elements of Chemistry in 1789. In it, Lavoisier described his discovery of oxygen and how it was necessary to support combustion. By carefully collecting and weighing the gases involved in this kind of reaction, he established the law of conservation of mass. He also included a list of 33 simple substances that could be combined to make compound materials. It was a pretty good list of what we today call elements, but he did mistakenly include heat and light as elemental gases, as well as 5 metal oxide compounds. In 1808, John Dalton gave the atomic hypothesis a big boost when he published a new system of chemical philosophy, which included the first table of elements with atomic weights. He determined these weights by assigning 1 to the lightest element, hydrogen, and calculating relative weight ratios of other elements through different chemical reactions. For example, he understood it took 1 part hydrogen and 7 parts oxygen by weight to create water, and he described these fixed ratios as being due to the discreteness of atoms and how they combine to form molecules. This was a big breakthrough, but the values turned out to be not very accurate due to 2 types of errors. Measurement errors, such as the fact that the weight of water molecules is closer to that of 9 hydrogen molecules instead of Dalton's number of 8, and what are called stoichiometry errors, such as assuming hydrogen gas and water molecules each contain 1 hydrogen atom instead of 2. Some improvements in the accuracy of atomic weights were made over subsequent decades with increasingly precise measurements. But it was not until 1858 that Italian chemist Stanislaw Cannizzaro corrected the stoichiometry errors of his predecessors to obtain a reasonably accurate list of atomic weight ratios. These results were communicated to the global chemist community a couple of years later at the first International Conference of Chemistry held in the Bavarian city of Karlsruhe. As one attendee, Lothar Meyer, later wrote, "Upon seeing Cannizzaro's paper, the scales seemed to fall from my eyes." Over the next several years, the ability to sort atoms into the correct order by mass allowed Meyer and many other scientists to notice that the chemical properties of atoms had repeating patterns. They imagined that these patterns were like a screw wrapping around a cylinder, notes on an octave scale, successive rings of a spiral, or just the rows and columns of a simple table. It was the simple format that Russian chemist Dmitry Mendeleev used when he first published his periodic table in 1868. He also published a revised table in 1871, which used the chemical periodicity he observed to accurately predict several missing elements in the repeating pattern. Over the next 15 years, gallium, scandium, and germanium were duly discovered with the chemical properties and atomic weights in line with his predictions. For his work, Mendeleev is frequently referred to as the father of the periodic table. Making sense of why atomic properties are periodic in this way requires a 20th century understanding of the structure of atoms that we'll explore more in future videos. But the key insights along the way were the discovery of the electron by J.J. Thomson, discovery of the nucleus by Ernest Rutherford, Bohr's atomic model featuring quantized electron energy shells, and Schrödinger's quantum mechanical description of electron orbitals. These developments finally moved atomic theory from a working hypothesis into well-established science. But enough about theory, let's look at some actual atoms. Going back to the example of atoms in a copper penny, let's use actual microscope data from scientists to see what it really looks like to zoom down to the atomic level of an object. Before we start, let me acknowledge this is a really odd-looking penny. It's actually from the 1830s, which was the last time pennies in the United States were made of pure copper. They're also called large cents because they're a little bit bigger than a modern US quarter or €1 coin. Pennies since the turn of the century have been minted from zinc and copper plated, and in case you're curious, despite the name, nickels are actually made of 75% copper. So since I want an elemental object to use for this demonstration, and copper is one of my favorite materials, I picked this really old penny. So let us start with 3 of these oversized copper pennies, and we'll leave the middle penny at actual size, at least on my 13-inch computer monitor. And as we zoom into the penny on the right, we'll be zooming out of the penny on the left at the same rate. As you can see, the shrinking penny is getting small pretty quick. So to keep a proper sense of scale as we zoom out, let's pause to put that penny someplace interesting. Let's pretend to throw it in Rome's famous Trevi Fountain. With that done, take a look at the penny on the right, which is getting pretty blurry now, so let's move over to a high-quality optical microscope. This copper is not really from our penny, but it's a sample of pure copper which has been polished and etched back to remove any surface contamination. In this image at 250x magnification, it's clear that the copper is not homogeneous, that is, it's not uniform looking. What you're seeing is that the copper is composed of individual crystallites called grains. And as you see, these copper grains come in different shapes, sizes, and colors. Some of them even look like they have stripes. The colors come from different orientations of the crystallites reflecting the microscope light differently. The stripes are actually places where the crystals are fused with mirror images of themselves, which is a common phenomenon in metals like copper and called twinning. Collectively, these observations describe what's called the grain structure or microstructure. The microstructure of a material will influence its properties like density, resistivity, and hardness, and it will depend on how the material was prepared. For instance, when coins are minted, the raw metal sheets are pressed between rollers to achieve the right thickness. This results in the grains getting stretched and elongated in the rolling direction as seen here. But then before the metal blanks are sent through the stamping machine, they're heated to make them softer so it's easier to strike the heads and tails patterns into them. During that process, the copper grains change shape again to be much less elongated as seen here. As we continue to zoom in, our pixel size is now approaching the wavelength of light, so we need to switch to an electron microscope which can image with wavelengths about 100,000 times smaller. Since I don't use visible wavelengths, electron microscope images are typically presented in black and white, but I've chosen to tint them for you so they still look copper-colored. In this imaging condition, the different copper grains have similar brightness, and the dark lines you see are the crystallite grain boundaries. Let's keep zooming in to look inside a single one of these grains. Here, at close to 1,000,000 times magnification, the dark areas you see are due to imperfections in the atomic packing arrangement, which are called crystal defects. Like other microstructural features, crystal defects impact material properties, and the density and type of defects is a function of the material processing. We'll take a deep dive into the science of crystallography in a future video. Beyond 5,000,000 times magnification, we are finally beginning to see the actual atoms that Democritus could only speculate on. The two lines you see here are twin boundaries like we saw in the striped grains earlier. The regular arrangement of copper atoms in this crystal form mirror images on either side of these two twin planes. As we zoom in, you can clearly see these atoms are arranged in a plane with hexagonal symmetry. Copper is a dense packed metal that packs the atoms in this configuration for maximum density. As we reach 150 million times magnification, we're close to the limit of what we can image with any microscope. Each copper atom is now 150 million times smaller than our penny, and if each atom were enlarged to the size of the original penny, that humongous coin would stretch across most of Europe. Before we leave these copper atoms, let me explain briefly exactly what you're looking at. It's a high-resolution transmission electron micrograph, or TEM for short. This means the copper had to be made extremely thin in this sample so the electrons could shine right through it to make the image, on the order of 10 nanometers, which is pretty thin, but not atomically thin. Each atom you see in this image is actually a column of many atoms which have just been tilted to appear as single atoms. If you want to see individual atoms in a TEM, you have to start with a sample that's only one atomic layer thick. This is very difficult to do with copper, but we can do better if we switch materials to carbon. Elemental carbon can exist in either diamond or graphite forms depending on how the atoms are bonded together. Diamond is famous for its hardness because it has a three-dimensional network of carbon atoms with very strong covalent bonds. Graphite is a layered material where those covalent bonds occur in two-dimensional sheets, but those sheets are only loosely bonded and can slide over one another, easily breaking off from the main crystal. This feature makes graphite a useful material both in pencils and as a lubricant. The 2010 Nobel Prize in Physics went to researchers studying unique properties of these two-dimensional sheets of carbon, which are called graphene. Believe it or not, the big breakthrough behind this Nobel was the use of Scotch tape to peel off atomically thin layers from graphite crystals in a process called exfoliation. The great thing for us today is this breakthrough led to an explosion of graphene research, including a lot of good microscopy. Here you can see one such image which is showing atomic resolution of a single graphene sheet. Unlike the copper sample we just looked at, this image is showing individual atoms instead of columns of atoms. Even more interesting is this research from Lawrence Berkeley National Lab, where they made an electron microscope movie of individual jiggling atoms. In this video, the same electrons that are imaging the sample are heating the graphene sheet to the point where the carbon atoms are literally boiling off a hole in the graphene. Here you can see individual atoms dancing around this inside edge before they evaporate by sublimation. So here then, in this simple video, is today's final demonstration of the atomic hypothesis.
Well, things are made out of atoms, little particles that move around, are in perpetual motion, attract each other when some distance apart, but repel being squeezed into one another.
That's it until next time when we'll continue our journey and zoom into the realm of subatomic particles. Thanks for watching.